Hello everyone. Welcome to this webinar on multiphysics analysis for medical devices with COMSOL. My name is Jennifer Segee, and I'm a technical marketing engineer working out of the Burlington, Massachusetts offices of COMSOL. I'm presenting today together with Nagi Elabasi. He's a managing engineer at Verist Engineering, an engineering consulting firm located in the Boston area. Verist provides services in product development, material testing and modeling, and failure analysis. Dr. Elabasi's primary area of expertise is modeling and simulation of multiphysics systems. He has extensive experience in finite element modeling of structural, CFD, heat transfer, and coupled systems, including fluid structure interaction, conjugate heat transfer, and structural acoustic coupling. He holds a PhD in mechanical engineering from the University of Toronto and held postdoctoral positions at the University of Toronto and MIT. We'll move forward now with our agenda for today. I'll begin with an introduction to simulation and, more specifically, modeling and custom application design with COMSOL Multiphysics. Then, Nagi will take over with the main presentation today, where he'll provide an overview of how COMSOL can be used to model medical devices, including relevant biological materials and physical processes such as blood flow, damage evolution, and electromagnetic heating of tissue. Nagi will show a live demonstration in COMSOL. You'll see how to set up a model of RF tissue ablation, analyze simulation results, as well as design and deploy simulation applications. Finally, there's the Q&A session, followed by a brief how-to. We would like to encourage you to submit questions at any time during the webinar. You don't have to wait until the Q&A session starts. Let's start now by looking at why you'd want to use simulation in the first place. If you're going to create a new product or process, you'll want to get the concepts right. Multiphysics simulation can give you valuable insight into how your product will perform. Simulation benefits the design and optimization stages, reducing the time and money spent on prototypes. And if you integrate modeling with manufacturing and quality assurance, you'll end up with a product that's much better understood and better characterized. Working together with the testing and manufacturing processes, simulations also allow you to test and verify the quality of your device or process. There are many unique benefits, though, to simulation in the COMSOL environment. COMSOL is a multiphysics as well as single physics simulation platform. It covers mechanical, fluid, electrical, and chemical simulations, or really any physics that you can think of. COMSOL is particularly well known for multiphysics or coupled phenomenon. And by this, I mean two or more physical effects that interact with each other and without limitation to the number of physics that can be included in a model. You can use the built-in physics interfaces available with COMSOL Multiphysics or define your own custom physics. You can combine, for example, electromagnetics, heat transfer, chemical reactions, fluid flow, and structural mechanics, enabling the simulation of complex multiphysics phenomena such as Joule heating, thermal expansion, convective cooling, RF heating, and fluid structure interaction. You'll also find that the COMSOL software provides not only the capability to set up your model and run multiphysics simulations, but also to design computational simulation applications based on your model, which have custom user interfaces. I'll cover simulation applications in more detail in the following slides. Today, you'll hear about how you can use COMSOL Multiphysics to model medical devices. More examples and applications of multiphysics simulations are featured in our magazine, COMSOL News, which you can read on our website. You'll find it in the resource gallery accessible from COMSOL.com. Now, let's explore the COMSOL desktop. Our interface is quite straightforward to use, where all the modeling steps are readily accessible and any settings can be edited as needed. You can do this in the window referred to as a model builder, then input or select your custom settings in the window just next to the model builder, and then visualize your results in the graphics window. Clicking on a specific physics node in the model builder allows you to view all relevant parameters and equations in the settings window. It's also possible to evaluate and couple several model components in the same file. Accessible from the home toolbar, we also provide application libraries with many helpful example models and applications. In case you're curious, the model featured on this slide is used to analyze the performance of a biosensor design, and it is available in the application libraries. You'll get a more in-depth look at simulation in COMSOL in Nagi's live demo later in the presentation. Here's the COMSOL Multiphysics product suite. All products can be used together to create many unique physics couplings. The products marked in blue represent physics and application-based modules. Those in green are multipurpose, and in yellow are products for interfacing with different CAD formats, software packages, and programs for data organization and visualization. For modeling medical devices, it's conceivable that any product shown here may be used. In this presentation, you'll see the use of multiphysics interfaces from several modules, including the AC/DC module, structural mechanics module, and CFD module. Now let's return to the console desktop once again, focusing on the application builder instead of the model builder described previously. The application builder allows you to create simulation applications from your console multiphysics models. Within just a few clicks, actually, you can have a basic app that's ready to share with your colleagues or customers. They do not need to know how to use Console in order to use the app that you designed for them, but they can still benefit from its modeling capabilities for product design. In your model, anything that's parameterized can become an input in an app. Then the value is selected by its user. The application builder features a form editor that allows you to customize the app's user interface by adding any input fields, graphs, tables, and many other features that are relevant to your model. An example of an app based on the biosensor model is available in the application libraries, and it's shown right on this slide. There's also a method editor that allows you to further customize the simulation app designed in Console, so there's a lot of flexibility there if you want it. A big question is, now that you've created a simulation application, how can you run it? While you can open and run an app from Console itself, it is also possible for other app users who do not have Console Multiphysics installed on their machines to run it as well. To do this, you'll want the Console server. Then an app user can install a Console client for Windows or use a web browser to run an application that's hosted on the server. This makes an app accessible worldwide, and any updates to the app are immediately available to the user. On this slide, you can see how the same biosensor app would appear in a web browser. Anyway, thanks so much for your attention thus far. Now, I'll turn the presentation over to Nagi, who will talk about modeling medical devices. Nagi.
Thank you, Jennifer, and welcome to everybody who is attending this webinar. So as you mentioned, Jennifer, there is a lot of benefits to computational modeling in any industry, and medical devices are no exception. Simply said, modeling and simulation help companies design better products in a shorter time. And in the medical device field, there's less room for errors or for huge factors of safety compared to other fields. So simulations are really helpful. And it is actually a very useful addition to existing sources of data for medical devices like human testing, animal testing, and bench tests. Simulation is a fourth important addition there, and in many cases, it is the most suitable option. And simulations are getting increasing recognition by regulatory authorities, so they're now commonplace in submissions to the FDA. And in many of these cases, you can do a single physics solution, and Console is good for that, but increasingly there's a need to put multi-physics because that's how nature is coupled. So I'll talk first about the different types of physics that you need for medical device simulation, then go over some of the challenges that are specific to medical devices, then examples, and then a live demo using Console. However, I just want to list the examples early on here so you can see what's going to come up next. There's an initial focusing in a microchannel example, RF tissue ablation, biodegradable bone screws, bubbles entrapped in a microchannel, and a compliant chamber for an artificial. I'll cover them briefly because there's not that much time. The focus will be to show you the benefits of using multiphysics modeling. There's one example, though, that I will go in depth into, which is the RF tissue ablation example, because that is also the topic of the live demo. So because of the diversity of medical devices, most or a lot of the physics available in Console is relevant. So for example, structural mechanics, relevant for cardiovascular applications, orthopedics and implants, wear, and the mechanical behavior in general of whether tissue or skin or blood vessels, or the plastics and polymers that make up the devices. The blood flow stimulation is also relevant for, again, cardiovascular applications, blood separation devices, and in some cases you can do single phase, multi-phase. I'll elaborate on that on one of the future next slides. Acoustics is also relevant, as you can imagine, for hearing aids and acoustic transducers. This is an example that you can download from the Console application gallery, Model 600, that shows you how to set up an FSI analysis of a blood vessel. Electromagnetics is also common for RF and microwave ablation devices and MRI devices. Heat transfer, again for RF and microwave ablation, infant incubators, laser treatments. The list is not exhaustive, but just to give you an idea of the common applications that use each physics. Species transport for drug release from implants and in any other drug delivery system. And the last item here is not a physics really, CAD import, but it really is important because there's a different forms of mechanical CAD formats that I'm used to, but there's also STL type CAD files for the irregular geometries like a heart or a lung or a bone, and COMSOL can import both of them. So that is an important, not physics, but still very important option to have. So now it's time for a poll question. Jennifer, can you present that?
Thank you, Nagi. So we'd like to hear from you, and this is our first of 2 poll questions. And in this poll question, please just take a few seconds to tell us, do you include multiphysics effects in your medical device modeling? Not yet. I work with one physics and I'd like to add more. Yes, but the physics are not coupled. Yes, the physics are coupled already. I would like to learn how. If you wouldn't mind just spending a few more seconds to let us know, we'd appreciate it very much. Okay, I'll close up in 5 seconds. All right, thanks so much, everyone. And just so you have some impression, actually, of how your peers are responding, I'd just like to share the results. And so what you'll see here is that 20% not yet and are working with one physics but would like to add more. 6% yes, but the physics are not coupled. 27% yes, and the physics are coupled. 47% I would like to learn how. Nagi, is that about what you would expect to see?
Yes, it is. Thanks, Jennifer. It's not surprising, and I guess if you were to ask the same question 5 years ago, there would have been less people using multiphysics and more single physics, and more people not using at all. So, and I expect that trend of increasing need for multiphysics to keep growing. So, to the next topic, these are the 6 challenges that I thought are relevant to medical device modeling. And the first 4, I'll go through in more details in the slides later on. These are the biological material modeling, blood flow modeling, how to model damage, and tissue heating resulting from electromagnetics. The last 2, the uncertainty and the variation from person to person in material properties is, I'll just mention it here. But it really is important because if you ask, say, or look or research for stress strain curves for an artery, you will see way more variation than if you were to look for a stress strain curve for stainless steel or rocks or polycarbonate. This is just the nature of the tissues and even the plastics and the polymers used to make the devices. But I'll elaborate now on the first 4 of these items. First, the biological materials. So these materials are typically involve complex stress strain behavior, including one or more of the following: large deformations, strain rate dependence, temperature dependence, anisotropy, and initial stresses or strains, and damage and failure. So they're not simple. And COMSOL has an extensive list of material models that you can apply to this, like a lot of selection for hyperelasticity. There's viscoelastic and viscoplastic as well. This is a nice example of an artery that you can again download from COMSOL that shows anisotropy in an artery. But chances are you're going to run across a material model that is not implemented in COMSOL or any other code that you use. So one option, there are 2 options actually for dealing with that in COMSOL. The first is just as you implement your own ordinary differential equations that capture the behavior of that material. Not trivial, but they're doable for certain. And there's a paper I presented at the COMSOL conference last year that shows how to do that for polyethylene. So that's one path. The other is to use the external material functionality. Now that is a new functionality introduced in 5.2, which allows COMSOL to link to pre-compiled user material libraries, whether structural or electromagnetic or whatever. But in this case, we are using it to link to PolyUMod, which is a material library that we developed here at Verist, and it has material models explicitly made for rubber and biological tissues and plastics. The second challenge is blood modeling, and you can imagine many medical devices deal with blood in one way or another. So accurate blood modeling is important, and so it's a complex tissue. It's composed of red and white blood cells and plasma and platelets, but in many cases it is sufficient or sufficiently accurate to model it as a single-phase Newtonian fluid. For example, if you're doing flow in a heart or artificial organs or a hemodialysis device, that in many cases is sufficient. You just have to be careful about the viscosity. It's a function of the composition, especially the hematocrit. But in many other cases, you just cannot use that assumption because it's not accurate. So especially if you have low flow rates or very narrow pressure vessels, then it's not that much Newtonian anymore, and COMSOL has some models for that, and again, you could implement your own models as well. And in some cases, you cannot even use a single-phase model. You need to use a multi-phase, and there are different options available in COMSOL. For example, if your device is involved in blood separation or segregation, like centrifuges, then it's no longer a single-phase model. Another issue with blood is that it typically affects the heat transfer analysis. So if you have a tissue, there's blood flowing through that tissue at a length scale that is not captured in the FEA model. So it's like flows through porous media. But it does affect the heat transfer. So it's typically accounted for using the bioheat equation, which is just provides additional heat, volumetric heat source or sink to the tissue. This is the heat generated. It's a function of the density, heat capacity, perfusion rate of the blood, and the temperature difference between the blood and the tissue. The third item on these challenges is the damage modeling. Now, it's important because, again, medical devices typically either are trying to fix a part or remove a part or treat a tissue, and one of the limits on how much power or velocity or force you can apply is that the blood or the tissue cannot take beyond a certain stress or flow rate or temperature. So it is usually important to model damage. And I listed here 3 or 4 forms of damage. First is in the tissue heating or cooling. There's damage, instantaneous damage if the temperature exceeds a certain value, whether high or low. And there's damage accumulation. If the temperature stays high for an extended period of time, it's worse than if it just stayed there for a fraction of a second. So there's damage accumulation. And both of these forms of instantaneous and accumulation of damage are pre-programmed in COMSOL. But again, there's no damage model that can work for everything, so you can easily implement your own damage model as needed. And here are 3 more forms of damage. The biodegradable materials, like you have biodegradable stents or sutures and stuff like that, they degrade intentionally in the body, and to get that degradation, you need to have advanced stress-strain material models that capture that. Another point is mechanical wear, for orthopedics especially. It's not, it's relatively easy to modify the contact equations in COMSOL to make it account for wear, and we did that in the paper that we presented 2014 at the COMSOL conference on using disc brakes as an example, but it can apply to any wear phenomena. And the last item is damage to blood. Blood cannot take a very high shear rate. So again, if the shear rate gets very high instantaneously, there will be damage. If damage can also accumulate for extended exposure of time to a certain shear rate, and we need to capture that. And the last item here on the challenges is the electromagnetic tissue heating. And there are 3 sources of heating that I will discuss, but the good thing or the interesting thing about this is that the time scale for the electromagnetic problem is typically much shorter than the heat transfer problem. So whether you're in the kilohertz range or the megahertz range, they're both much faster than a typical heat transfer problem. So that allows a time averaged heat source from the electromagnetics rather than having to do a transient electromagnetic analysis. Makes things way more efficient. So I'll go now over the three sources of heat loss. The resistive heat loss, basically if you have an electric field and the material has a certain conductivity, a current is generated, and the heat resulting from this is the expression you see here on the right. Also, there's dielectric losses, and there's several ways to model that. But if you're assuming that you have a frequency domain model for the electromagnetic problem, then that is best translated into a complex relative permittivity. So the permittivity epsilon r, instead of being just a real component, has an imaginary term, and that imaginary term is the one that contributes to heat loss, and it's also a function of the applied frequency. Same for magnetic losses, maybe common than dielectric losses, but there are medical applications where they are relevant. Same thing, we use the same approach, just modify the permeability to have a real and an imaginary relative component, and the imaginary part is again the one that affects the heat loss. And these are pre-programmed in COMSOL as well, so that makes it straightforward to use them. Okay, so now back to the list of the examples that I showed earlier. Let's start with the first one. So this is inertial focusing on a microchannel. The idea here is that particles suspended in flow under the right conditions will migrate across streamlines to reach certain equilibrium positions. And the forces acting on these particles are two. There's a shear gradient that pushes the particles one way, and then when the particle gets close to the wall, there are repulsive forces that push it another way. So I'll show an example on the next slide, but the idea behind this is that you can isolate the cells, such as cancer, and then that helps deal with them. So we did an CFD model in this case, but with additional equations to track the motion and the rotation of the rigid particle within the flow. So here's another illustration of this concept. If you have a straight channel, flow going from left to right, particles are shown here in red. They come in random. They will come out under certain conditions to be in the middle at two locations you see here. Now, if that channel was curved, then you have a random inlet again. You will have the particles focused at this point. And if the velocity or the curvature are different, you will have different focal points. And that was the purpose of this investigation. This is actually part of work done by Joseph Martel, and we helped with the modeling of that. And we have you have a reference here where you can get more details from his work, and also a COMSOL news article that we published with him and his advisor in 2013. So here are some experimental results to compare with the simulation. The agreement was very good. The first line here is the straight flow. So D number 0 means it's a straight flow, and the higher the D number, the higher the curvature. So in this case, random flow comes in here, and you see it's focused where we expect it to, with a certain curvature of the channel. You get the focusing actually at two locations, here and here, and you see the simulation predicting exactly the same thing. And at higher curvature, you get that one point only where the particles get focused. So the simulation was in good agreement, and once that you have that, you can use it to try way more scenarios than you can with an experiment. And one last slide on that example. This is just showing that at some point for some configuration, these are the velocity contours in a curved channel. This is the particle, and these are the traction forces acting on it. The resultant in this case was a force to the left, so it's still not in equilibrium, and at some point that resultant will drop to something very small. Oh, on some configurations there's no equilibrium configuration as well. That was part of the investigation. So the next example is a bone screw, and it's made of a biodegradable material. So this is the bone screw here. So the material is PLLA in this case. It's a viscoplastic material, non-linear, and has damage and degradation. We did not model at this point the degradation, just even in the version state. Still, it's a complicated model. And these biodegradable materials also used for stents and sutures, so very common. And the focus of what I'm going to show here is not the simulation results for this case, but rather the material model that captures the behavior of the PLLA accurately. So we use the polymod library that links now through the external material functionality, and this is the simplified rheological representation of the material model. It's not really springs and dashboards, but it's a 3D version of that, if you want to visualize it. So it has a hyperelastic element in parallel with a hyperelastic element, again, that is in series with a power flow that has double exponential yield evolution. And we could have added more networks, but we found that when you put just these two, you get a very good fit to experimental data, which I will show in the next slide. So this is the stress strain data in uniaxial tension for the PLLA. And experimental data is in solid line, and the simulation prediction is in the dashed line. Red is at a relatively high strain rate, not that high, but relatively high, and the blue is at a much lower rate. So you see the material is strain rate dependent, the two curves are different, and it's not something that you can fit to a simple material model like you see here, but the agreement between material and the experiments is really good. And we took it one step further. We did some cyclic testing on that same material. So you have you start from zero, you load it up, and you hold for 3 minutes, and load it up again, hold for 3 minutes, and then unload and reload and keep loading. So it's a complex loading path. But again, the dashed line, which is the prediction from the model, is in very good agreement with the that complex material behavior. And the next now is this is now a different example. It's involves a lab-on-a-chip device that detects the concentration of certain minerals in the blood, and that device performance suffers when air bubbles get trapped in the channel, especially where the sensors are. So this is not the real geometry. This is just a lot of modifications, but it still captures the same concept that was a problem in the real device. So we use COMSOL basically to find the conditions that lead to the air bubbles to stick in the sensor surfaces. You cannot prevent some cases bubbles to originate, but if they don't stick, then you're good enough. So that is the function though of the geometry, surface tension, and the contact angles between the bubble and the different parts of the channel. So we did these two simulations, one where there's a 90-degree contact angle at the constriction here, and the bubble will not stick, it will keep going. If the angle is much smaller, then you will have the entrapment. The bubble will get trapped here. And that is not even accounting for differences between advancing and receding contact angles. In some cases, I know though that you can have analytical estimates to determine whether the bubbles will stick or not. In some cases, you need simulation. And my colleague here at Verist, Matt Hancock, is an expert in that area. So the fourth example is the artificial lung compliance chamber. So basically, if you have an artificial lung connected to a pump, it's better in some cases to have a compliant chamber between them, and that lowers the inflow resistance and reduces flow pulsatility originating at the pump. So we developed this idealized model based on the paper that you see referenced here. It was a 2D axisymmetric FSI analysis. The blood comes in from the bottom, comes out from the top. This is the compliant chamber. And depending on the specific design, you may want to model the airspace around the chamber, because that could be in a pressure-controlled chamber, so that would affect the performance of the compliance chamber. So to illustrate the behavior, we put a 0.1 millisecond pulse, a little bit longer than 0.1, but and that is the blue curve, and monitor how the flow at the outlet. And you see the green curve; it is much smoother, so that sudden change in velocities and flow rates that may result from a pump has not been transferred to the lung. And also the compliance of the lung is lower, of the system, sorry, is lower when, especially at high frequencies. So COMSOL, this was done with COMSOL, but also if you want to put this compliance chamber in a system level model, it's typically done through a RC circuit type representation, where basically a resistor and a capacitor represent that compliance chamber. We use COMSOL to get these parameters, which then you can use in a system model. Last slide on that example is showing the velocities through the chamber. That it starts here. That's the 0.1 second pulse that starts at the bottom. Let's see when it starts again here. and you see it dissipating by the time it reaches the top. So this end will not feel the big change in flow rate. Mind you, though, the displacements you see here are exaggerated, so it does not displace that much. A scaling factor was used so you can just visualize what happened. Now, there's one more example, the RF tissue ablation example, but before going there, I just want to talk a little bit about our company, Verest Engineering. So we are COMSOL certified consultants. We work extensively with COMSOL, but we're also independent. So, and we use other simulation tools. It so happens, though, that for many of the problems you see that we come across, COMSOL turns out to be the most suitable. This is just a collage of some analyses we have done in the past. And we do also other things. We do mechanical testing, especially for polymers, including high strain rate, high temperature testing. We do reliability and failure analysis. And you can imagine the combination of testing, failure analysis, reliability, and simulation gives us good insight that we have to help our clients with design problems. We also offer COMSOL-related courses and polymer-related courses. So there's a course coming up in April, which is exactly on the topic of this webinar. It's a 2-day course. We go in depth into all of the issues I touched upon here in the webinar. I teach it together with Stuart Brown, the managing principal here, and we devote time to go over specific problems that the attendees may have, because medical devices is a very broad field. And we have courses, like I mentioned, also in the finite element and modeling and testing of polymers. So that's it about Verest. Now I think it's time for a second poll question. Jennifer, can you please present it?
Thank you, Nagy. All right, we'd like to hear from you one more time. Which multiphysics effect is most relevant to your medical application? Tell us if it's fluid structure interaction, electromagnetics with heat transfer, heat and mass transfer, or other. If you don't mind just taking I'll keep this open for about 5 to 10 seconds. So you have an opportunity to get your response in. All right, I'll close it up in 3 more seconds. All right, thanks so much. And once again, I'll share the results. That way you can see how your peers are also responding. So we have 43% fluid structure interaction, 28% electromagnetics with heat transfer, 13% heat and mass transfer, and 17% other. Nagy, is this about what you were expecting for medical devices?
Yeah, that is not surprising. So the example here is more focused on the electromagnetic heating, but we find a lot of FSI. If I was to list one case that gives us the most request, it is FSI analysis. So yeah, not surprising. Thank you, Jennifer.
All right, I'll hide this up, and you can continue forward with your presentation.
Thanks. Okay, so that's now the last example, the RF tissue ablation. So the example I selected, I wanted to make it different from the one in the COMSOL gallery that you can download. So here it involves ablation of tissue that is adjacent to a blood vessel. So if it's heart tissue, for example. So you need the CFD or flow analysis together with electrostatics and the heat transfer. So this is the probe here, the blood is in here, and this is the tissue you're trying to ablate. And the figure on the right shows how ablation works in general. So the very short summary of this is that there's a region of tissue that you want heated up. So you apply an electric current at a high frequency to that region through either a single electrode like you see here or double electrode. That's the less than 1 minute summary of how this works. And there are a lot of challenges specific to tissue ablation, and these are load application. The easiest is if you have an applied voltage, you just put it in the model, straightforward. But if you have current control or power control, that's not straightforward. You need to, you can do it through setting up scalar equations that control the applied power, especially if the resistivity and the electric conductivity changes. The other thing is material properties. It's hard to get accurate properties that vary within the temperature range and frequency range you're interested in. So there's a need for more validation tests than is in other cases. And there's the normal person-to-person variation and the difficulty of getting these properties experimentally. So validation takes a big part of that effort. Also, boundary conditions are a challenge because there's no perfect contact between the electrode and the tissue, or sometimes there isn't. So there is electric impedance and there's thermal impedance, and getting those accurately in some cases is important to the accuracy of the model. Sometimes they're not, they're not relevant. So it's, but if they are, then you need to test further to try to find out what are the correct values. Also, if you have a single electrode design like the one in the previous slide, then you need to put a proper boundary condition for the far field. If you have two electrodes, that's relatively easier. And the last item is the damage modeling. I'm not going to repeat that because it's what I mentioned earlier. The instantaneous and the damage accumulation are both there. And if you want to know more details about how you can use COMSOL for tissue ablation, there's a very good blog that came up a few weeks ago on January 20th by Walter Frey at COMSOL. You can check that out. It has a lot of the details that I'm talking about and more. And there's this example, the hepatic tumor ablation, which again you can download. It's COMSOL application ID 497. So to the specific model we have here, the solution steps were as follows. First, a stationary fluid flow analysis just to get the blood flow around the electrode, and then the electric field analysis, and then the transient heat transfer analysis. Now, if there's no change in properties, that heat transfer analysis can actually be decoupled from the fluid and the electric field analysis, but in practice, the conductivities change, and also even the density, but most likely the conductivity is the one that changes the most, and maybe the viscosity. So you need to couple them in many cases. So just for demonstration, we applied a voltage for 20 seconds, followed by no power for 10 seconds, and the properties are not exactly the right ones, but just to give you an idea of what you can do with COMSOL for RF ablation problems. So a little bit on the results, and then I'm going to go to the live demo. So this is how the blood flows. The streamlines coming in from this side. You see they go around the electrode. No surprises there. This is an animation showing the temperature variation with time. You see it being non-symmetric. So the downstream side heats up more because there's less efficient heat transfer through the fluid. I'll let that play one more time. We have the damage variable activated, so you can plot it here, and you see that damage is localized very close to the tip of the electrode. It's not symmetric, and it also does not reach 100% for the parameters that I selected here in the simulation. Damage also increases versus time. This is damage versus time, the blue curve, and the maximum temperature versus time is here. Okay, so time for the live demo. It's a big model, so I'll try to just show the part that show how to set up the model, how to get the results, how to post-process, and how to develop applications, because it's really straightforward. So now I'm going to switch over to COMSOL. Okay, so there is the model. Let's see. So the geometry, let's start with the geometry. It's pretty straightforward. So I was able to do that here with just COMSOL, no imports of CAD. Basically, the electrode is 2D, drawn in 2D here, and then revolved, and then the block for the tissue and a block for the blood. And you'll see that the dimensions for most of these are given in terms of variables: tissue width, tissue depth, and these are parameters that you can just modify in here, and it rerun the analysis, and change them, and the model will be updated, because that it's not that, I think I made it smaller than it should be, just so that it runs a little faster. So that is the geometry creation. Then let's see the materials. There's blood, insulating material around the electrode itself, and the tissue. And for the tissue, you'll see it for the properties, the electric conductivity, it has an equation. Sigma tissue is a function of T, the temperature. So if that function is defined here, a value basically at 0 degrees and a value at 100 and linear interpolation between them. It could be anything else, but it does vary significantly over a 0 to 100 temperature range. So that's the material properties. Next thing is the electric current. So there are three physics: current, heat, and laminar flow. Electric current applied everywhere, so that's all shaded blue here. There's the voltage applied at this step here, and then there's the impedances. So this, because this is a single electrode, we have to put proper impedance for at the boundaries of the model. I just put a value here, but this has to be checked carefully. At the impedance at the boundary of the tissue, and also impedance at the boundary of the blood. There's also impedance between parts. This is between the electrode and the tissue, and also between the tip of the electrode and the tissue, and between the blood and the electrode. But that's it. That's all the physics that's needed here. The bioheat equation is applicable also to the whole geometry. What you see highlighted in blue here is the tissue model, and there is an option to activate these damage quantities and put your limits for when damage happens. For the solid, the electrode, there's no need for that damage, so just regular heat transfer in solids. And for the fluid, just regular heat transfer in fluid, and it gets the velocity field from the laminar flow, which I'll discuss next. I'll minimize that. And laminar flow is only to this part. I just put simple boundary conditions like inlet at this end, outlet at this end, and I put symmetry here. Again, something can be done more accurate, but for the purpose of illustration, that's good enough. And there's a node that console adds here for the types of multiphysics coupling, and it gets automatically populated. So there's electromagnetic heat source that couples the heat with the electrical equation, and there's non-isothermal flow in the fluid. Temperature affects flow and vice versa. You can add other forms of coupling if as needed, and then it will take care of the rest. Next thing is the mesh. I could have probably just selected default mesh and be done, but in some cases it's good to have manual control over the mesh. So you'll see the commands here. Give it a second. Yeah, I made a mesh that maybe a little bit too fine, but finer here where you need to, a little bit coarse on the outside, with a boundary layer at the edges where there's interface between solid and blood. So again, a finer mesh, a coarser mesh would have been fine, but it was straightforward to mesh that. And then the studies. So the first was this stationary study, and that links to the second study, which is a transient study, which goes from 0 to 30. Uses the results of the stationary study. Pretty straightforward to set up. And then the results, which you've seen many of them in the slides I've shown earlier. One you didn't see, which I think is important, is this. This is the heat source. The heat flux from normal to the surface of the tissue. So this is the surface of the tissue. Tissue is below, blood is above, and you see it's non-symmetric. So really, you need a CFD analysis to get that. Basically, more efficient heat transfer at the downstream, at the upstream end of the flow rather than the downstream. You can only capture that if you actually have the CFD. And I'll show just the ease of just creating plots by creating one more. Let's say at time 15, we want to look at a volume plot. No, sorry, let's delete that. We want to look at streamlines, let's say. So streamlines of current moving forward only, and on the starting on the surfaces you see here highlighted. The current that starts here, how is it going to flow? That's basically what I'm trying to see. And you see it flows out this way. To make it look more beautiful, I like to say, let's say 0.5 millimeter radius, let's say, and plot again. Oops, too much. 0.1. So you see the current that starts here is going to spread that way. Let's put like 64 of the streamlines, so it looks better. And that plot would look better if it has a if you see the electrode highlighted. So I'm going to plot electrode. I just defined a subset for the electrode, and let's make it not red. Let's make it gray. So it kind of shows a little bit better this way. And you see how easy it is. And for example, the streamlines are red now. Let's say I don't want it to be red. I want the color to be more useful. So here they are now, proportional in magnitude to the velocity, to the voltage. You can make anything else, but so it was, as you can see, relatively quite straightforward to generate that. And in the next couple of minutes, I just want to show one more thing about this, which is how easy it is to create an app. So I created this app, which I'm going to show you first how it works. That took a few minutes. And I'm not an expert in app development. We have other people here who do that way better. But it just shows which variables to expose, which plots to show, and it's just someone can use that without having to be an expert in COMSOL, and that's very helpful. I like to predefine some views. So if you switch view, and oh, that was two already. If you switch view, you get the geometry changed. If you change the electrode radius and plot geometry, you see it right away changing there. So it's really straightforward to develop the app. And this is what it looks like. Let's say I want to add another plot, just from one of the existing plots that I have. I just insert object, button, place it where I want it. It's too small. Let's make it bigger, and let's give it a picture. There, and put it here. And let's make it point to one of the plots, the one that gives the maximum temperature versus time. It's here, and say plot, and tell it to go to graphics 1. And that's it. Hopefully now if I test the application, if I did that right. Yeah, there it is, and click, and it works. That gives you the maximum temperature versus time, and that was pretty straightforward. So that's it for the stuff that I wanted to show in the live demo. I'll take it back now to COMSOL, to the PowerPoint, sorry. So I have one more last slide. So basically the advantages of COMSOL are extensive capabilities, ease of model setup, flexibility to add your own equations or material models, and the application builder that makes this stuff really easy to distribute to a wider audience like designers, manufacturing engineers, and test engineers. So now back to you, Jennifer, for the QA.
Thank you, Nagi, for this excellent demonstration and presentation today. We have quite a few questions, so we'll move right along, starting with the ones that we heard most frequently today from all of you. The first one being, how do you validate the results of a numerical model?
Oh, thanks. Yeah, no, there's several things that we do for that. So we do a lot of model verification. That is to make sure that the solver, the analysis settings, the mesh are all properly selected. Then for verification, we compare the results against any experimental data the client might have, even if that involves simulating different bench tests or animal tests. And in many cases, we request additional testing to evaluate material properties that may be relevant to the accuracy of the model. And we can, before requesting that, we can look at the sensitivity analysis to see, like, if you change the material property within reasonable range, is it going to make a difference or not? So we're not just doing experiments for the sake of experiments. So that's how we do it.
All right, thank you, Nagi. So for another very common question we had today, how do you determine the thermal and electric impedance between electrode and tissue?
That depends on the materials, the contact pressures, and the roughness. So we typically estimate upper and lower bounds of these values based on the problem. And like I mentioned for the previous question, we can sometimes just test these bounds, see if they make a difference. And if they don't, it's good. If they do, then we got to do custom experiments to obtain these values, and or maybe calibrate to existing bench data and so on.
Okay, for this next question, I'll start it off, but feel free to add anything to it. We hear, just for curiosity, what is the difference between COMSOL Multiphysics and the additional COMSOL modules? With COMSOL Multiphysics, it's going to come with base functionality. So depending on, it's everything that you need to actually set up and solve COMSOL Multiphysics models, as well as the applications that Nagi just demonstrated. However, if you need kind of more detailed functionality, additional built-in physics interfaces for a specific application such as AC/DC or structural mechanics or RF or any of the examples that you actually see on the slide in front of you now, that's when you're going to want to add an additional module onto COMSOL Multiphysics. So you start with COMSOL Multiphysics and you can add on additional capabilities as needed. And in addition to physics-specific or application-specific modules, there's also modules for interfacing, so that way you can interface with CAD programs, MATLAB, Excel, and many other programs. I don't know if you'd like to add anything to that, Nagi?
Sure. We did probably just like Jennifer mentioned. We start with the basic, and through the years we've been adding modules, because if you want something, let's say in the nonlinear structural materials module, it's just sometimes you can implement your own stuff, but really the modules have very good functionality, and we've been through the years adding a lot of modules.
Okay, all right, so for our next question, for the bubble entrapment example, can you use the moving mesh method to track the bubble boundary?
Yeah, good point. Yeah, you can use that. We use the phase field multi-phase method for other reasons related to the problem, not what you see here. But if the topology of the bubble or the droplet or whatever it is not changing much during the simulation, then you can use the moving mesh method, and it's available in COMSOL, and it's much faster if the problem can fit the restrictions, which is the topology not changing much.
Okay. For this next question, in your demo, in the end part, you were just showing how to set up simulation applications, and someone asks, how easy is it to add features to the application you showed?
Oh, it was easy. I mean, I showed one case where you just add one more result, but what I didn't show was that initially, when you have the model and you like it and you want to start the app, COMSOL guides you through the, what variables you want to expose, what results you want to put, and so on, so that that initial barrier to setting up the app is overcome, and you put the main stuff is easy, and then adding stuff is easy, like I showed for this one result item that I added. Jennifer, you want to add something to that?
I think the only thing that I did want to just to kind of reiterate is that in setting up an application from a multiphysics model, you do that using the application builder, and that is a feature that's already available in COMSOL Multiphysics. It's not something that you have to add on through purchasing another module, for example. When you set up that app, it has an easy-to-use interface, and the idea is to be able to then share it with your colleagues or your customers, and to do that, then you would use the COMSOL server. And the COMSOL server, I wanted to point out, has the functionality of COMSOL Multiphysics, but it doesn't have the user interface that you would use to set up the app, to set up the model. It's what you would use to actually host the application so that someone can run it. But then someone would ultimately actually access it through a COMSOL client for Windows or actually through a web browser. And so I just wanted to make sure that you knew about that as well, pertaining to not only what you would need to set up apps, but also for someone else that you want to provide access to, what you would need in order to give them access. Okay, so for our next question, Can the custom material model developed for the bone screw be used with any type of multiphysics problem in COMSOL?
Yes, they can. I mean, now that with this external material functionality, you can use the PolyMod or any other library in any COMSOL model. And we've, of course, tested it for structural problems, but also for FSI and other coupled problems.
So we also heard, does the standard COMSOL example set include any medical device examples? And I'll say very quickly that it does. I don't know if you want to point out any specifics, Nagi, based on some of the questions that we're getting, but we do include some by default.
Yeah, I mean, I try to include in some of the slides, there's the FSI analysis of the blood vessels, there's this ablation example, and there are many more, yeah. So there's a good number, and the good thing about these examples, you get the model, you get the step-by-step description of how, what's behind the scenes and all that. They're really helpful.
Okay, so for our next question, let's see. Can COMSOL simulate the deformation of an artificial heart valve?
Yes, it certainly can. It's an FSI problem. The difficulty in that kind of problem, in my opinion, is that when the valve is closed, that blocks the flow. So it's not easy to have a flow volume that contracts to zero, but it's doable. There are ways to handle that in COMSOL, so it's pretty well suited for this type of problem. Yes.
Okay, so I'll just take two more questions today. The next one, I need to model wound healing. Does COMSOL have pre-programmed parameters for skin or wounds?
I'm not aware of any, but if you have the equations, I would imagine they're like rate equations. They're ordinary differential equations, not partial, so they're relatively easy to implement if they're not there already.
Okay, so for this next question, for blood flow modeling, have you integrated the effect of surfaces physicochemistry, which can be important effects and affect the results of your simulations?
No, we haven't. With blood flow modeling, it is really a huge range of possibilities out there, and we find that for most cases, really, the Newtonian single phase is okay, but we have a case with blood separation where we need to account for stuff that I mentioned, but we didn't have something where we need to account for surface chemistry. That would be interesting.
Okay, and then just one last question, and I'll take this, but certainly feel free to add anything about your experience with it. Is COMSOL able to store its plots and the related data? And is it possible to link that with Microsoft Word? So you may have noticed now that since Nagi has done the live demo, that there is a results node. And under that results node, your plots are organized, and you're able to also export those from COMSOL, as well as perform a whole range of post-processing to them. So as far as Microsoft Word, we do offer live link to Excel. And so I hope that will also suit your needs. And you can see that on the product suite on the slide that's currently showing in the section that has the yellow bars on the top. I don't know if you want to add anything to that, Nagi?
No. Thanks.
All right, so I'm going to wrap this up now. Thank you, Nagi, for answering pretty much most of the questions, and of course for your presentation and demo today.
My pleasure, thanks.
All right, so moving on, a question that we hear quite often is about how to try out COMSOL Multiphysics. And one way is to join us at a workshop. Our workshops are free hands-on events where you can meet a COMSOL specialist and try COMSOL Multiphysics with their guidance. Next up, COMSOL Days. These are one-day conferences held around the U.S. and globally. These events include multiple mini-courses, invited speakers, as well as networking opportunities that will leave you ready to start using multiphysics modeling and build simulation applications with confidence. Next, save the date for the COMSOL conference. These are 2- and 3-day events available at 8 locations throughout the world. Attend to meet with colleagues and multiphysics simulation experts, expand your knowledge and discover new features through dozens of lectures and hands-on mini-courses, and realize your full potential to innovate by using a simulation-driven design workflow. Registration will be open soon. Go to comsol.com/conference for more information about event dates and destinations. You can also sign up to be notified once registration opens. On our website, you'll also find helpful information about Multiphysics and our products. And there's more. You can find user stories, a model gallery, the ComSol blog, and a discussion forum. If you're looking to update your current version of ComSol Multiphysics or ComSol Server, or try it out for the first time, go to comsol.com and under the section called Support, select Product Download or Product Update. If you'd like to speak with us directly, just contact us at comsol.com/contact. That's it from us. Thanks again, Nagu, for your presentation.
Thank you.
And thank you, everyone, for your attention. Have a great day.